Hey everybody, I hope this video finds you well. In today's video, we're going to continue on with the topic of expected value. We're just going to look at a couple examples of calculating expected values and using those to determine if a game is a good or bad idea to play. So the first example that we're going to do here is based off of a very sort of common sort of game that can be found in a lot of casinos. It's going to be a sort of modified example about a slot machine. So let's suppose that you visit a casino that has the following slot machine. The slot machine consists of 4 wheels. So 4 wheels spin around, and on each of these 4 wheels, there are 5 images. So there's a spade, heart, club, diamond, and dollar sign on each of those wheels. And then depending on the sort of combination of images that come up, you may win or lose money. So according to this, if 4 dollar signs all show up, you win $200. So you could sort of think about that as the jackpot. If you get 4 diamonds, it's also pretty good. You win $100. If it comes up with 3 dollar signs and 1 diamond, you win $50. And if it comes up with 3 diamonds and 1 dollar sign, you win $10. If it comes up with any other combination, so if it comes up heart club dollar sign or diamond dollar sign club spade, anything like that, you lose $1. So there's a couple different ways to win, and everything else causes you to lose $1. So what are we going to do with this? Well, we're going to start with what we always start with whenever we're doing expected value, which is that we're going to build a probability model. Always need to build a probability model because we need to know the outcomes and their probabilities before we can go to the expected value. Then we're going to calculate a couple probabilities. We're going to calculate the probability that you lose money on one play of this game. So if you just had money to play once, what's the chance that you lose? And then we're going to talk about what is the probability that you go on a horrible losing streak and you lose money on 25 plays of this game in a row. Then in D, E, and F, we're going to turn to the expected value. We're going to calculate and interpret the expected value and decide if this is a good game to play. Then we're going to interpret the expected value if you were to sit down and play this game 300 times. And then finally, we're going to figure out how you would modify this jackpot in order to make the game fair. Okay, so let's go ahead and do this. So the first thing we need to do is we need to talk about the probability model. So let's talk about the outcomes and their probability. This is where we got to start anytime we're doing expected value. So the outcomes are if you get 4 dollar signs, we know that that's like a plus 200. If you get 4 diamonds, we know that that's a plus 100. We know 3 dollar signs and 1 diamond, that's a plus 50. And we know 3 diamonds and 1 dollar sign, that's a plus 10. Everything else we know is a minus 1. Now we need to fill in these probabilities. Well, this is a little bit harder than some of the ones we were doing in the first video, just because calculating these probabilities, we sort of need to know how many different things can happen with these 4 wheels and all these different images. So we're going to use a little bit of our counting stuff. If you think about this, right, we've got 4 different wheels here, right? So we've got our sort of 4 wheels. All right, how many choices do we have on each of these wheels? Well, according to this, each of the 4 wheels all have 5 images on them. So we've got 5 choices, 5 different things can show up on each of these. We know from our section on counting that whenever you have multiple options and you have multiple selections, you need to multiply to count up the number of total options. So if we do 5 times 5 times 5 times 5, we should see that we'll get 625 total things, meaning there are 625 different things that can show up on this slot machine. Those are things like spade, spade, club, diamond, or spade, heart, diamond, dollar sign, or spade, club, club, dollar sign. All of those, if we were to make a list, there'd be 625 different things. So that tells us the denominator for all of these probabilities is going to be 625. All right, how many of those give you 4 dollar signs? Well, that should be very simple. There's only one. The machine would literally have to look like dollar sign, dollar sign, dollar sign. So that probability would be 1 out of 625. There's only one thing where we would end up with 4 dollar signs out of those 625 possibilities. What about the 4 diamonds? Well, that would also be 1 out of 625 because the only way that the machine could look would be diamond, 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 diamond. Okay. What about $3 signs and 1 diamond? Well, there's actually some different ways. If we try to write those out, Could be where you get all the dollar signs and then a diamond. Or it could be that you get a couple dollar signs, then a diamond, then a dollar sign. Could be that you get a dollar sign, then the diamond, then a couple more dollar signs. Or you could even start with the diamond and then get all dollar signs. And we know these are all possible because according to the information up here, each of the four wheels have all of the images. So the diamond can show up on any one of the four wheels. So the probability here then would be 4 out of 625. Well, the same logic should hold for 3 diamonds and 1 dollar sign. We can imagine what those would look like. It would be like diamond, 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 and then a dollar sign, or diamond, diamond, dollar sign, diamond, or diamond, dollar sign, diamond, diamond, or I guess you could get the dollar sign first and then get 3 diamonds in a row. So there's 1, 2, 3, 4 again. So that probability would be 4 out of 625. Now, as we know, these are all pretty specific types of things. Losing can mean lots of things. It's anything that isn't one of these. So to get this probability, we'll need to just take whatever is left over. Because if you remember, this has to be a probability model, meaning that these probabilities need to sum up to exactly 1. So what do we have here? We've got 1, 2, 6, 10. So we've used up 10 different outcomes. That means the remaining ones, 625 minus 10 is 615, must be how you lose. So the probability of losing is 615 out of 625. And if you check 1, 2, 6, 10, 625, yep, that does make a true probability model. So the chance you win the big jackpot is 1 out of 625, the small jackpot 1 out of 625, these ones 4 out of 625 and 4 out of 625, and the chance that you lose 615 out of 625. All right, so this is our probability model. To be honest, once we have this, most of the other work should come pretty easily. So let's go ahead and calculate a quick probability. For B, we want the probability that you lose money on one play. So probability, lose money on one play. So you're going to play the machine once. We want to know what's the probability you lose money. Well, the only way you lose money is right here. So that probability would be 615 out of 625. Or I suppose if you really wanted to, you could figure out that as a decimal, just to have a better sense of the size of that number. 615 divided by 625 would be 0.984. So if you sat down and you only had one play of this machine, there's about a 98.4% chance that you will lose. Okay, let's go ahead and do C. Let's calculate another probability. What is the probability that you lose money on 25 plays in a row? 25 plays in a row. So we need this to happen 25 times in a row. So we're going to multiply this with itself 25 times, which means we're going to raise this to the 25th power. So we can calculate this as that 615 out of 625 raised to the 25th power. And if we calculate that, well, we should see that that comes out as about 0.668. So this is sort of scary about this machine. This tells us that there's about a 66.8, almost 67% chance that if you sat down and you played this thing 25 times in a row, you would lose every time. Now, does that mean that it's guaranteed to be a bad game? Not necessarily. We know that if you lost 25 times in a row and then you won this guy, that would be great. You'd lose $25, then you'd win 200. You'd be happy with that. So this doesn't necessarily tell us that this is a bad game, but this is not a good sign. This certainly means that you could sit there for quite a while and have a good chance of losing every time. To actually determine if this is a good or bad game, let's go ahead, move on to D, and actually calculate the expected value. So we'll do that on the next page. To do that, we want to get the expected value. I'm going to really quickly just carry over the sort of model that we got here. So let's see if we can just grab that real quick, just so we don't need to rewrite it. Okay. Let's see if we can just copy that guy. And we'll just pop this guy over here. Okay. There we go. So now we don't have to rewrite that. We can expand it a little bit, I suppose. Okay, so that's our model that we had there. So let's just take that, and we want to calculate the expected value. So how do we get that expected value? Well, the expected value here, we'll just zoom in a little bit. The expected value, remember, is going to be we take each of these outcomes, multiply it with its probability, and add all that up. So you could get plus 200, but with only a probability of 1 out of 625, plus 100, 1 out of 625, plus 50, 4 out of 625. And you'll notice that I'm not bothering to write the plus here. You don't really need to write the plus in these ones. Obviously, when you don't write anything in front of it, it just means that the number is positive anyway, so we don't need to write that. Plus 10, 4 out of 625. And you know what? We need a little bit more space. Let me just go back and rewrite those a bit smaller. Sorry about that. Let's go ahead and just rewrite that. That's 200, 1 out of 625, plus 100 times 1 out of 625, plus 50 times 4 out of 625, then plus 10, 4 out of 625, and then our last one, that minus 1 and the 615. So plus minus 1, 615 out of 625. So we put all that into our calculator and we get our expected value here. So 200 times 1 divided by 625 plus 100 times 1 divided by 625 plus 50 times 4 over 625. And then the last few. Okay, looks like that should come out as negative 0.12. All right, what do we look at first here? Well, we notice the negative, right? So we can say that the expected value less than 0 implies this is a bad game. So from our perspective, this is a bad game to play because it is negative. From the casino's perspective, obviously, they would love us to play this game because from the casino's perspective, since this is bad for us, it is good for them. But it is a bad game from our perspective. How bad? Well, 0.12 in terms of money is going to be $0.12 or 12 cents. So we could say we expect to lose 12 cents per play on average. So if we were going to sit down and play this machine, we are expecting to lose about 12 cents per play on average. So if we played this game lots and lots of times, we're expecting that as we play it longer and longer, the average loss is going to be about 12 cents per play. Okay, let's go ahead and maybe give ourselves a little bit more context to work on that with. All right, let's say expected value after 300 plays. So we're saying now, say we know that we're going to sit down and play for 300 times. What do we expect to have happen? Well, we know that you're expecting to lose about 12 cents per play, and you're going to play 300 times. So what we're going to do is we're going to say minus 0.12 per play times those 300 plays. What does that give us? Negative 0.12 times 300. That looks to be negative 36. So after 300 plays, we expect to be down around $36. So in other words, if we sat there and played 300 times, we'd expect that after those 300 plays, we'd be down around $36. Now, this should tell you something. This means that if you sit there and play 300 times, you're going to have some moments where you win, right? If you lost every time, you wouldn't be down $36. You'd be down $300. And we're saying that that shouldn't happen. If you sit there and you play 300 times, you might get one of these bigger jackpots, or maybe you get one or two of these smaller ones. But you would lose so much more frequently that once you put all your winnings and your losses together, we'd expect to be down somewhere around $36. And you can see that all of this is basically saying that the longer we play, the worse and worse it's going to get for us. If we did this as the expected value after 3,000 plays, this would be negative 360. It would be even worse because the longer we play, the more and more we lose. And if you think about it, that's the entire way that the sort of casino industry is structured. Their idea is that maybe a single person shows up, puts $1 into the machine, and wins $200. Sure, that person's super happy. But from the casino's perspective, there's thousands of people playing thousands of times. And as more and more people play and as the machines are used more and more, we know that in the long run, it's going to be bad for those players and good for the casino. So while an individual person might throw $1 in, get really lucky and win $200, this overall analysis is showing us that the casino is still going to benefit because people in the long run, or people on average, are going to be losing money. All right, last little thing to do here is we wanted to know what would make this game fair. We know from this analysis here that the game is bad to play. So how would we make it fair? So let's talk about what should $4 pay to be fair. Okay, well, let's go ahead and remember what fair means. Fair in this context means that the expected value needs to be 0. So we want to try to modify this payout to make the expected value 0. So obviously, since the game is bad, this is too low, and we know that it has to be a higher value than 200. So whatever our answer is should be higher than $200. Let's see how to solve it. What we're going to do is we're going to set up this same formula for the expected value, but we're going to set this expected value to be 0, and we're going to take this 200 and let it be a variable so we can figure out what the $4 should pay. So to do that, we're going to say 0 equals x times 1 over 625 plus 100, 1 over 625, plus 50, 4 out of 625, plus 10, 4 out of 625, plus minus 1, 615 out of 625. Now we just need to solve this equation for x. Easiest way to do that, I mean, you can just use your calculator if you want, but you can do a little bit of cleanup. All of these have a 625 in the denominator. So let's multiply both sides by 625. If you multiply both sides by 625, if you multiply 0 by 625, that's not going to change, so we'll get 0. When you multiply this side by 625, you multiply every term by 625, which is going to remove the 625 from the denominator. So in this term, we'll just have x times 1, which is just x. On this term, we'll have 100 times 1, which is just 100. On this term, we'll have 50 times 4, which is 200. And we'll have 10 times 4, which is 40. And then finally, we'll have negative 1 times 615, which is negative 615. Putting that stuff together, 100 plus 200 plus 40 minus 615, you get 0 equals x minus 275. Add the 275 onto the other side, 275 equals x. So $4 should pay $275 to be fair. Now, why do we care about this? Well, in some ways, you can think about this as the tipping point. If the casino sets any big jackpot less than 275, so they put 274, 273, anything less than 275, we know the game will be a bad game. If they set anything higher than 275, they put 277, then the game will become good, because exactly at 275 would make the game fair, meaning that the expected value is 0. All right, so that was a little bit more complicated of an example than some of the other ones we did with expected value. Let's look at one more that uses something, a very special technique we learned from probability to analyze some expected value. All right, so we've got one more example here. We're going to suppose that you visit a carnival that has a bucket toss game. So this game is pretty simple. What you do is if you pay $5, so you got to pay $5 to play, they give you 5 shots. You've done apparently some independent bucket toss research, and you know that you can make 45% of your shots and that each shot is independent. All right, we know that the payouts for this game are as follows. If you make all 5 of your shots, then they give you a big prize worth $40. If you only make 4 out of the 5 shots, they give you a medium prize that's worth $20. If you make 3 out of the 5 shots, you get a small prize worth $10. Otherwise, so if you only make 2 shots, 1 shot, or none of the shots, they give you nothing. So we want to do the same thing we did in the previous one. We want to build a probability model, calculate a couple probabilities, and then talk about the expected value. Okay, so let's go ahead and talk about how we're going to do this probability model. So for A, we want to talk about the probability model. So we've got the outcomes, and we need to figure out their probability. So what are the outcomes? Well, if you make 5, that would be, well, it would be worth $40. Is that really the outcome to us, though? Well, we got to be very careful here. The first thing we should recognize is that this game costs you just to play. So it says for this game, you pay $5. So we need to make sure we take that into account. So if you think about it, this big prize, well, you pay them $5 and then they give you something worth $40. So what is that to you? Well, we would consider that a plus 35. All right. What about making 4? If you make 4, you give them $5. Then they give you something worth 20. What is that to you? That's plus 15. You could also make 3. So you give them $5. They give you back something worth $10. To you, that's a plus 5. Then we have our otherwise. The otherwise, you give them $5 and they give you back nothing. What is that to you as a net? That is negative 5. So we had to be a little bit careful here and modify each of these values by the cost of playing the game because that wasn't done for us in this one. If you quickly look back at the previous example, you can tell that that was already done because the otherwise had you losing $1. So the cost of playing the game in this one must have already been factored in. You can also tell just because in the wording of the problem, there was no mention of how much it costs to play. So that means it's already been factored in for you. So just be very careful if you're ever doing one of these problems and you see something where it talks about how much you have to pay to play, you're going to need to modify the values. Okay, what about these probabilities here? Well, to do these probabilities, we want to call our attention to something else very important. We have this word independent here. We know independent was our tip-off for thinking about whether or not things were binomial. So let's do a quick check. What do you need for binomial? You need 2 outcomes. Well, there are definitely 2 outcomes here. Every time you take one of those shots, you either make or you miss. We know that it's independent. So those are good. And then the last thing you need is you need to know how many times you get to do it and your probability of success. Well, we know you get to take 5 shots and the probability of success, 45%. So we have n equals 5, probability of success, 0.45. You can also make a note that 1 minus p, the probability of failure, 0.55, right? If you have a 45% chance of making it, you have a 55% chance of missing. So let's fill in these probabilities using this binomial. You can also remember we had a binomial formula, probability exactly k successes. It was this formula, NCK, p to the k, 1 minus p to the n minus k. Remember, this counted up the ways it can happen. Probability of success to the number of successes, probability of failure to the number of failures. So let's use that right here. All right, so making 5, that's going to be 5C5. 5 successes, we need all of them to be successes. Probability of success, 0.45 to the 5. 0.55 probability of failure, can have 0 failures here. Let's go ahead and calculate that. If you wanted to, you could just write this simply as 0.45 to the 5 because this is 1 and this is 1, but you can just go ahead and use the full formula if you like. So once you type that into your calculator, you should get that that is approximately, and since the numbers are pretty small here, we'll save 3 decimals, 0.018. So you only have about a 1.8% chance of walking up there and making all 5. For making 4, you would have 5C4, 5 attempts, you have to make 4, 0.45 to the 4, 0.55 to the 1. 4 successes means you get to have 1 failure. You type that into your calculator, 5C4 times 0.54 to the 4 times 0.55, and you should see that that comes out as a 0.112. Oh, sorry, 113. once you round. So you've got about 11% chance of making 4 out of the 5 shots. All right, last one, 5C3, or second to the last one, excuse me. 0.45 to the 3, 0.55 squared. So we type that in, 5C3 times 0.45 to the 3 times 0.55 squared. And you should see that that comes out as about 0.276. Now, for this last one, we could go ahead and continue using this formula, but we'd have to use the formula like 5C2, 0.45 squared, 0.55 cubed, plus 5C1, so on and so forth. Because this would include making 2, making 1, or making none. The easier way is to realize that this is the last outcome, so these things have to sum up to 1, so we can just take these away from 1. So we can do this as 1 minus 0.018 plus 0.113 plus 0.276. And if we do that, we can get the probability that we don't get anything. And you should see that that's 0.593. So, in other words, what we're saying is you've got about a 1.8% chance that you win the big prize, about an 11% chance that you get the medium prize, and about a 27.6% chance that you get the small prize. There's about a 59% chance, though, that you walk up to this game, you pay your money, and you get nothing. Now, this means that you have a higher chance of losing than you have of winning. But if you think about it, those wins are worth a good amount of money, so that doesn't necessarily mean that it's a good or bad game yet. We'll have to calculate the expected value to do that. All right, before we do that, though, we have a couple questions about the probability, so let's go ahead and do that. We want to do the probability that you win a prize on one play. So maybe you only have time to go play this game once. What's the chance that you walk away with a prize? Well, notice we're saying win a prize, so it doesn't matter if it's big, medium, or small. We can just add the probabilities together. 0.018 plus 0.113 plus 0.276. Add those together. 0.018 plus 0.113 plus 0.276. And you can see that that's 0.407. So there's close to a 41% chance that if you only get to play this thing once, you will walk away with some prize. Notice that this guy is 1 minus this guy because this is the chance you walk away with nothing. Okay, let's calculate another probability. What's the probability you win a prize 3 times in a row? So what's the chance that you go up to this game, you play it 3 times, and you win a prize all 3 times in a row? Well, we know that this has to happen 3 times in a row, so we're just going to take 0.407, raise it to the third, 0.407 cubed. That comes out as about 0.067. So there's only about a 6.7% chance that you would walk up to this game, play it 3 times, and win a prize all 3 times. Now, those prizes could be small, medium, big. We're just saying that you would win some sort of prize 3 times in a row. All right. None of this still tells us whether or not it's good or bad because we still haven't made use of these values. So let's go ahead and actually calculate the expected value. To do that, once again, we'll sort of grab our probability model here because we'll definitely need that. Okay. Let's go ahead and copy that, and we'll go on and finish this up over here. So let's go ahead. We'll just paste that guy in. Okay. So there's our probability model. So for D, we want to get the expected value. So what is the expected value going to look like here? Well, we take each of these outcomes, multiply them with their associated probabilities, and add them up. So 35 times 0.018 plus 15 times 0.113 plus 5 times 0.276 plus negative 5 times 0.593. We put all that into our calculator, 35 times 0.018 plus 15 times 0.113 plus 5 times 0.276 minus 5 times 0.593, and your expected value here should come out as 0.74. First thing we will look at whenever we see an expected value, positive or negative. Well, the expected value here, my Apologies, that looks a little messy. Okay. Expected value here, greater than 0, implies this is a good game. Right? That's basically saying that we expect, in the long run or on average, to make money when playing this game, right? In other words, right, that it is beneficial to play this thing. How good is it? Well, we expect to win 74 cents per play on average. Now again, that on average phrasing is super important. When you walk up to this game, one of 4 things is going to happen. You walk away with the big prize, meaning you netted $35. You walk away with the medium prize, meaning you netted 15, or you walk away with the small prize, which means you netted 5. Or you walk away with nothing, which means you lost 5. You will never win 74 cents. There is no cents even going on here, right? It's all in dollars. But this is telling us if you sat there and you played this game a long time, many times, your average would come out to basically gaining 74 cents per play. So this is basically telling us what the structure or the nature of the game is like. All right. For E, I think we gave ourselves sort of a long term. I guess you have a lot of time on your hands. And yep, you sit there and you play this game 50 times. What do we expect to have happen? So this is the expected value after 50 plays. So we know that you have 0.74 per play times those 50 plays. And if we do that, 0.74 times 50 comes out as 37. So after 50 plays, expect to be up around $37. Again, not guaranteed to be exactly 37, just to be around that mark. So that means if we sat there and played 50 times, we'd have some times where we'd win the big prize, the medium, the small, a lot of times where we would lose. But once we put all those winnings and losses together, we'd expect to be up somewhere around $37. All right. So these 2 examples sort of run you guys through just some more practice of calculating expected value. In the next video, we'll finish up this section on expected value and finish up the section on probability overall by just talking a little bit more in depth about exactly what we mean about on average or in the long run. So we'll have sort of a theoretical discussion to finish up this big topic of probability plus expected value.